My name's Jess, and a bunch of other stuff. I make algorithmic art, which is I make computers do things that I think are pretty. I want to show you a train of thought I had, I guess it was the beginning of this year, about some ways to use some technologies that are ubiquitous because they're in the web browser, but that you might not know about even if you're a web developer. All right. One of those is WebGL, which lets you run code that runs on your graphics card, right? And the metaphor for WebGL is that you write two programs, one that renders points in space, and the other that renders color values, and you mix them together and you get colored objects, and that's what 3D is based on, right? You can use that to make 2D graphics by rendering a flat plane and then doing colors on top of that. A lot of people do that. There's this community called ShaderToy where people just write fragment shaders that write colors on a flat plane. And a popular thing to do there is to re-implement 3D algorithms. So they're doing 3D programming on top of 2D programming on top of 3D programming for some reason. Okay. And the other technology I'm using is the Web Audio API, which is super complicated. It's this design by committee thing. I'm only using one class from it, which is the script node processor, which is actually deprecated, but they haven't replaced it with anything, so it still works. This is a Hello World program of web audio. I have a script audio node that is attached to the output, and I'm just filling the output buffer with a sine wave based on the time times 2 pi times 440 hertz. So you get concert A. Let's try actually making a sound. Yeah. Okay. And the neat thing about audio processing is if you want to combine more than one sound, you can do that by just adding them together. So this is the sum of just 3 sine waves. Okay, it's a chord. So you can think of audio as a function from time to a numeric value. And in digital world, where we talk about samples and samples per second, CD quality has this magic number, 44,100 samples per second. Okay, but in JavaScript, calling something 44,000 times a second is too much overhead. So the Web Audio API has this idea that you're going to make a frame of audio that's a little bit of a distance into the future. So a reasonable one would be a 1K of samples at a time. So then you're only calling your function 43 times a second, which is much more reasonable. Okay? And so analogously, you can think of video, like WebGL video or anything, as a function from time to a 2-dimensional array of colors. And that has a frame rate, that's how many frames per screen, of like 24 to 60 is comfortable video. And I noticed that 43 frames a second that my audio code was running was like right in that numeric range for frames of video. And I was like, is there a way you can bridge the gap between these two concepts? And what I come up with is if you throw away the color data, the data structures look very similar. In fact, every row of video looks like it could just be a sequence of audio. And because adding 2 audio signals together makes them play at the same time, if you just sum up the columns of video, then you can play it all at the same time. So I wrote some JavaScript that does that. This is the whole thing. It renders a WebGL program to a flat plane, reads the pixel data back into main memory, iterates over it, summing up the columns. There's a little bit of algebra to get the numbers in the right range because it's graphics is in 0 to 256 colors, and audio is like a floating point clamped around 0. And then, excuse me, this is a fragment shader program that does the same sine wave, still sine of time in seconds times 2 pi times 440 hertz. But now the x-coordinate is part of the time calculation. And instead of just outputting the value, I'm using the y-coordinate to decide whether to show a black or a white pixel. So that looks like this. So that was a picture of a sine wave and the sound of the same sine wave. Sorry, it's a little loud. I can actually turn that down. See, that's better. Okay, so why is that moving? Well, at that frequency, it's a certain number of samples long when it repeats. And so that's a certain number of pixels wide. And the screen is a different number of pixels wide, and so it's offset a little bit every frame of video, so you get the illusion of motion. You can make a sound that, you could pick a wave that fit the window perfectly. This one. That's 43 point blah, blah, blah hertz. This is actually, yes, making a sound that doesn't come through sound systems very well, because that's It's actually kind of low and rumbly. You're getting a resonance there. But you can take it up a few octaves, just have a regular note. This is kind of a weird frequency. It's not a musical note. It's like a little bit flat from F, but it's the resonance frequency of this box on my screen, and so the wave just fits perfectly. This is the same code. It's like it would be moving if it was different, okay? And even though it's not a musical note, you can still do music with it, because music's all about ratios. So you can do a chord that's just waves of relative sizes, because music is all about ratios. So this is a major scale. It's just take an arbitrary frequency. You can have an array of notes. This isn't how we do it in modern music. This is the classical way of doing it. Now we use square 12th roots of 2 to calculate these, but I think the integer ratios make more sense or more intuitive. Okay, so I was thinking about this pitch, 43 point whatever hertz. I thought, that's a really weird number. That's CD quality divided by 1K. That seems so like modern and arbitrary, and maybe no one would have ever found a use for it before. So I Googled it, and I found that that wasn't true. There's this chiptunes artist called Adventure Kid who has all this amazing synthesizer math that goes way in depth, and you should check it out. It's way over my head. But he also, one of the things he has that I thought was really cool, and what he's sort of famous for, is that he distributes this pack of what he calls single cycle waveforms that are shapes you can use instead of a pure sine wave to make different sounds. You play the same note, but with instead of just a perfect sine wave, you have some other pattern, you get a different timbre. And so all sorts of synthesizer equipment can import these files and play sounds. And he distributes them as .wav files, and I thought that was cool, and I wanted to listen to them. But I don't have a fancy digital synthesizer, so I thought, well, if I write some code that translates WAV files into images, and then I display them in my browser, then then I could hear what they sound like. So I wrote a Ruby script. These are some of the WAV files as PNGs, basically. The gray is 0. White sections are positive numbers, black sections are negative numbers. And these are all piano sounds, and they sound like this. Okay? So while I was doing that, a friend of mine sent me a text message that was a recording of her newborn baby making sounds, making cute baby sounds. And so I did the obvious thing with that and ran it through the same. And that has this nice repeating pattern. It actually just goes and goes way longer than the screen can show. But so I saw that pattern, I cropped it out. So what does that sound like? So it's sort of an oboe sound, but that's part of a human voice. Her vocal cords were making all these sounds, and it went through that for like a millisecond, and now I have this new instrument based on that. And so I thought that was really exciting, and so I got out my phone and I recorded myself, and I went, ah, ee, ooh. Okay, so I'm going to try to show a demo that mixes these ideas together while I talk just a little bit more. This piece is called Blue Skies and Red Trees. And I didn't actually write this as music because I'm not really that much of a composer. I have, whoa, thank you. I have each of these voices doing this short loop of different notes, but they're all the lengths of these lists are relatively prime with each other, so it gradually iterates through all the possible combinations of sounds. And I thought that was pretty clever, but I knew I wasn't the first person to think of that, so I asked a friend who's a music major, what do you call it when you do that? And she said, well, it's basically minimalism. That's exactly how Steve Reich's clapping music works, or Terry Riley's NC, where you have people just sort of iterating through small musical sections, getting novel combinations as they go. I have some ideas of what to do with this, beyond this. There is a web MIDI standard. You can plug in an actual instrument and have it control the browser or vice versa. It's weird, but it works. I'm not much of a piano player. I have actually gotten a demo of that, but it's not very exciting because you have to listen to me play piano. Also, the math for synthesizers is this really deep field. It's 60, 70 years old now. I've only scratched the surface of that. I'm sure it's super interesting. Wow. I don't know why it's longer. I'll just turn it down. I was thinking about other geometries. If you use circles and you have lots of different resonance frequencies, and maybe that'd be interesting. And anything that a computer can do is fair game. So this is a visualization of the rounding errors of floating point numbers. It looks like something, so it must also sound like something. I haven't actually tried to play it, though. And then when you're thinking about video and audio signals, eventually you remember we used to send them down wires with electrical analogs. And I started asking, what would happen if you just plugged an old camcorder into a speaker? What would you hear, and could you control it? And the answer is kind of. This pattern, muting it. This pattern looks better than it sounds, but it does sound vaguely musical. So I have this list of links that are the things I refreshed obsessively as I was building this. The first 4 are all WebGL references that are just really great. Mozilla has the best web audio API documentation that I found, actually, and that's really good. And I've got AdventureKit and another chiptunes artist who have synthesizer math resources on the web that you should check out if this is interesting to you at all. I wanted to thank my friends who listened to all the terrible noises I played at them, including everyone who was at Bang Bang Con last spring, where I had a version of this that was loud and noisy in a different way, and all of you tonight also. So thank you.